Welcome back, everybody. In this video, we'll be taking a look at Ohm's law and applying it to a current carrying wire. Let's take a look at the problem statement. The figure gives the electric potential V of x along a copper wire carrying uniform current from a point of higher potential 120 microvolts at x equals 0 to a point of zero potential at x equals 3. The wire has a radius of 2 millimeters. What is the current in the wire? I reproduced a graph up here of the voltage versus position. And so beneath it, I've also drawn the wire kind of matching up with the graph. And so on the left-hand side of the wire, we have a voltage of about 12 microvolts. And then on the right-hand side of the wire, we have a voltage of about 0 microvolts. And the question is asking us to find the current in the wire that's traveling as a result of this potential difference across the wire. And since we're dealing with something that has currents and voltages and something that's resistive as the wire itself is, then most likely we're going to have to use Ohm's law. There's two forms of Ohm's law, and so I'll write them both down over here. The first form relates the current density to the field. And so the first form I'll write as current density equals the field divided by the resistivity. You can also write this in terms of conductivity, which is equivalent. And then the second form of Ohm's law is probably the more familiar one to you, which is that the total current, is given by the change in voltage divided by the actual resistance of the wire. It turns out for this problem, since we're given about the same information for both of these equations, either one of them will be about the same amount of work. So we'll do both of them one at a time. Let's use the first one. And so say I'll try J equals E over rho first. Now what are we given in this problem? We're given that we're given that the resistivity, we know it's a copper wire, and the resistivity is a material property which doesn't depend on what the wire looks like or how big it is or how it's bent or what the width of it is. It's an independent material property that only depends on the fact that this wire is made of copper. So that value for the resistivity will be tabulated in books and online, and that value is approximately equal to, so resistivity of copper is approximately equal to 1.69 times 10 to the minus 8 ohms times meters. Okay, now this equation doesn't have the current explicitly in there, it has current density. So, and those are related by the fact that the current density is the current per unit area. So if I just write that down, and then if I replace this in that equation, I can get rid of the J and then instead have an I in there. So let's go ahead and combine these two equations, and we'll find that the current divided by the area equals the field divided by the resistivity. Solving for the current, we have that the current equals the field times area divided by the resistivity. Now, what do we know and what are we looking for? So we're looking for I. We know the resistivity. We can find the area because we're given the radius of the wire. So if we can solve for that, pretty straightforward. We are missing the field, though. So we have to figure out how we can find the field given what we know. And I want you guys to do that on your own. Find out how you can find the field, and the hint is to try to use this voltage graph, the voltage versus position graph. So take a minute, do that on your own, and pause the video now if you need to. The relationship that we can use here is that the field is related to the voltage in the following way. The field is a spatial derivative of the voltage. So let me write that down. Technically, it's a negative spatial derivative. So in this case, we're actually given the voltage graph as a function of position. So to find the derivative, we can just inspect the graph differentiated at any given point. And fortunately, this graph is linear. So the derivative is just equal to the slope. So to find the derivative, we just find the slope. In this case, the best way to do it is to use the endpoints. The voltage change is minus 12 microvolts, and then the position change is 3 meters. So the field value is 4 microvolts per meter. Now, before we finish this problem up computationally, let's take a minute and kind of think about this physically in terms of what's actually happening as far as the current is flowing. So what I want you guys to do on your own is determine the following things. Which way is the field pointing? Which way is the current flowing? And then finally, which way are the actual physical electrons moving? Take a minute now and pause the video if you need to. First, let's look at the field. The field points in the rightward direction. We can see this in two different ways. First, it's a positive quantity, so it's pointing to the right. More physically, the field always points in the direction of decreasing voltage. So we have a higher voltage on this side and a lower voltage on this side, and at every given point, the voltage is decreasing, so the field will always point in the direction of decrease. So the field will point in the rightward direction. Now the current is defined as to always point in the same direction as the field. This is a definition. So by definition, because the field points to the right, the current also points to the right. But these both indicate which way positive charges would move if they were placed in this field. Now, what's actually happening in the wire is that electrons, which are negatively charged, are physically moving. So those are going to be pointing in the opposite direction. So actually, in this wire, the voltage is decreasing from left to right, but the electrons physically in the wire are moving from right to left. All right, so that's the basic physical picture. Let's finish up the problem and get a numerical answer. You have all the tools to do that here. We have the field value. You can find out the area, and we have the resistivity. So go ahead and plug in those numbers and find a value for the current, and we'll come back and check that after the break. So finishing up the problem, we have, again, let me just rewrite what the equation was. We had this, so we just got to plug in the values here. And I'm not going to write in all the values here, but you can find the answer on the solution posted online. The area is pi r squared, and r is given to you. And then the field we found a moment ago, which was 4, I'm going to go ahead and convert it to SI units. So it's 4 microvolts per meter, so I wrote that as 10 to the negative 6. And then finally, you're dividing by the resistivity, which we also had written down. And so when you carry this calculation out, you get approximately 2.97 milliamps. And so that's the answer. That's the current that's flowing through this wire based on its potential difference and the geometry of the wire. Now let's go ahead and do the same problem but using the other form of Ohm's law. I'm just going to set it up for us, and we'll see that the answer is going to be identical, so it doesn't really matter. The amount of work will be about the same in each one as well. So let's now use the second form of Ohm's law, which is that the current is equal to the change in voltage divided by the resistance. In this case, we're looking for the current, so that's already in the equation. We have a graph of voltages, so we can most likely find this delta V. We don't know what the resistance is. We do have a resistivity, so let's relate those. Now, the resistivity is the independent quantity. And again, that only depends on the fact that it's copper. But the resistance depends on what the wire actually physically looks like. And they're related as such. The resistance equals the resistivity times how long the wire is divided by the cross-sectional area. So as you can see, this obviously depends on geometry because you've introduced geometrical factors there. But you know how long the wire is, and you know what the change in the voltage is over the wire. And we know the cross-sectional area. So again, we can just plug in the values we have here. And what you'll find is that the current equals delta V. And if I just invert this, times A divided by rho L. And you'll see that this is basically the same thing as over here, plugging in the values. So let's go ahead and summarize what we've done here. We were given a graph of voltage versus position and asked to find the current. First, we applied Ohm's law, J equals E over rho, to the situation. We use a relation between current density and current to rewrite J in terms of I. Then we use a relation between voltages and electric fields to find E. Alternatively, we began with I equals delta V over R and rewrote R in terms of rho and the geometry of the wire. Well, I hope this was a useful video in applying Ohm's law to current carrying wires. If you have comments or questions, please leave them on the link attached to the video, and we'll see you next time.